chain rule, and I love calculus 2.5, the chain rule. I love this rule because like it's so beautiful. Yeah, I still don't know the proof for it, so I'll probably research that a little bit later. But let's start with a function like f of x equals x squared plus square root x squared plus 1. So how might a normal person go about this? I mean, not a normal person, because a normal person would know the chain rule. But how would someone um, who's a little experienced in math go about this? Well, if it was me, I would say, oh, look at this term right here. Maybe you can just square root both sides, or sorry. Whoa, okay. Maybe you can just do x plus 1 to the 0.5, which is just 1, because you could just cross out the square roots. But again, that's not how algebra works. In fact, this is not a difference of squares at all, so you can't even do that. So if we start here at this function here, there's no way to simplify this really algebraically. I mean, you can try doing um, x plus 1 over x. You can do other things, but it's like, what do I do here? How would I take the derivative of this function? And this is where a beautiful thing called the chain rule comes in. And the chain rule has to do with composition of functions. That's all it is. Chain rule is just dealing with f of g of x. They'll use some different other notations later on, but really this is all what the chain rule is, and that's why I find it so beautiful, because they managed to figure it out with composition of functions. So let's go back to the original function, and again, you can also write the chain rule as f of u, where where u is its own function, where u equals g of x or something. So let's go back to the original function, which is x squared plus 1. I can rewrite this as square root u, where x squared plus 1 is equal to g of x, which is equal to u. Pretty beautiful. And then I can write this outer function as just a square root f of x equals square root x. Such that f of u would equal square root of x squared plus 1. Because all I'm doing, or f of g of x, all I'm doing is plugging this into the square root function and getting this, x squared, yeah. It's really beautiful. Love that. So let's go ahead and differentiate the first function. But before I do, I want to go over what it really means. So that means the derivative of that function right there, so the derivative of f of g of x, which I guess would be that, is equal to the derivative of f. Wait, hold on. How would you actually write this? It's a little bit strange. Oh, actually, yeah. Yeah, okay. So this is how you would write it. Derivative of h of x is equal to the derivative of h. How would I? Okay, the derivative of f of u plus the derivative, or times the derivative of u, which I guess would be the best way to put it, because this function is composite of f of u and g of x. Or you can write it as the derivative of f with the g of x remaining inside times the derivative of g of x, which is the chain rule. In fact, this is a little bit complicated, but I'll show you in a second here. So let's go back to the other function, and we have square root x squared plus 1. Again, you can't simplify this algebraically, or at least I think so, because maybe there's a way, but I'm not too sure about that. Actually, this would have imaginary roots, so no. What's this function? And again, as we've mentioned before, we can write this as f of x equals square root x, while u is equal to square root x squared, or sorry, not square root x squared plus 1, x squared plus 1. Just so that when we do f of u, it's equal to the composite function, which would be, let's denote it as h of x actually. So h of x is equal to square root x squared plus 1. Such that f of u is equal to h of x, because you just plug the u into this, which gives you square root x squared plus 1. So again, the derivative of h of x here would just be the derivative of the first, or the outer function, which will be the square x because it's the very outer function. So the derivative of f of u times the derivative of u, which we'll just do there. So what's the derivative of f of u? where we keep u inside constant. So let's go over here to square root x. What's the derivative of square root x? Square root x would just equal to 0.5, and let me put that in parentheses, x to the negative 0.5, and then you could simply just replace u back here because again the chain rule states that inside it stays the same. So you just replace u back here to get x squared plus 1. And that's the first part, and then you just take the derivative of u, which would just be 2x here. So this is all you need, and you can simplify this to x over square root x squared plus 1 if you really wanted to, but really that's the logic behind the chain rule. So again, I know it's a little bit complicated because it comes out of nowhere and you don't know really why it works, but you just have to apply it really. I mean, there's a lot of things you're not going to understand how it works. In fact, in chemistry we learned about Boltzmann's and Josiah Willard-Gibbs equations, and many chemists in the world don't know how that works. So yeah, sometimes you'll just have to apply things without working. So let's use a simpler function. I mean, I don't know if it's simpler actually, but it's sine x squared. So let's identify the outer function. I'm going to give you guys a second here. I would say like 5 seconds. So okay, well, I guess you could have just paused it. So the outer function would just be f of x is equal to sine of x, and g of x is equal to x squared, such that f of g of x, which is equal to h of x, which is just the function together, or y in this case, is equal to sine of x squared, because all you do is plug, again, the function into x, if you guys know about composition of functions. So there's that. So how do we take the derivative? Again, the derivative of h of x is just the derivative of f of g of x, or where g of x equals u and g of x. And if u is equal to g of x, this is just equal to f of u times u. So again, it's whatever notation you want to use. This one is probably a little bit more precise and accurate. I mean, they're probably the same thing, but again, this one uses the actual function notation instead of like a variable like u. So again, it's just the derivative of the inner function, or the outer function, times the derivative of the inner function, but when you take the derivative of the outer function, the input stays the same and does not change. So, I was going to actually delete everything, which is probably a bad idea, because I would have to write it again. So again, I'm just going to put this in the corner, just so you understand the steps that I'm taking. So yeah, the derivative of h of x is going to be equal to the derivative of f of g of x times g of derivative of g of x. So what's the derivative of f of g of x? Because we're trying to find h of x. Again, derivative of f of x is just equal to sine x, or cosine x, sorry. And the derivative of g of x is just going to be equal to x, 2x. So again, remember, you just keep the input the same. So it's going to be cosine x squared times the derivative of the inner function here, which would just be 2x. So 2x cosine x squared should be your function. And again, it's right. But now we get to something called the power chain rule. And again, it's the same exact thing. I don't know why they say it is, or do it as a new concept. So now I'm not going to have the rule in the corner. So now you're just going to have to follow along using what you learned. So un equals nu n minus 1. Pretty simple, where u is an elementary function. So let's take the function x cubed minus 1 to the 100th power. Again, what can we break this down into? Well, I can break it down into a polynomial and a power. So the first function, and that's the very outer function, which I guess would be the thing you evaluate at the end. So this 100th right here. So f of x would be x to the 100th power, and g of x would equal to x cubed minus 1, such that f of g of x is equal to h of x, which is equal to x cubed minus 1 times 100. So again, just decomposition of functions, simple right there. So maybe I will keep the rule in the corner. So it's just going to be that derivative of h of x is equal to f of g of x times the derivative of g of x. But you can use u again like they're doing here. I mean, whenever you see u here in my video, it's just going to be equal to g of x. So let's take this here and let's differentiate the function. So if we want to differentiate the function, all we do is differentiate the outer function, and the outer function is going to be here, so it's going to be 100. And then remember, the variable gets replaced by the input value, which is 99, because again, just the power rule here. And then times the derivative of the inner function, which is just 3x squared. This will be simplified to 300x squared times x cubed minus 1 to the 99th power. And that is your first derivative. Again, differentiate the outer function and keep the input the same, and then times it by the differentiation of the input. I'm going to keep that top thing there so you guys can see it again, because I don't want you to forget the chain rule, which can get quite complicated later on. So yeah, it's beautiful, really. So let's go over something where you'll have to use the chain rule and the quotient rule. So maybe it's a little bit difficult for you, but whoa, okay. So x squared plus x plus 1, and this is the third root of it. So we can break this down into two functions, and it's going to be f of x equals, hold on, I'm looking at this actually. See, let's not do this one, because on my notes it appears that I wrote something wrong. So we'll do g of x equals t minus 2. I hate when they use t actually, because when I do my homework and they use t, I write t like 20 times and it gets confusing. And then t's get mixed up with pluses. So like this is it. Yeah, so I'll switch out the variable to x, just so it's a little bit easier to see. I love x. 2x plus 1. Do that, and then we'll put it to the 9th power. So again, this is just a power tower. I mean, I don't think it's called power tower. It's a power chain rule. So again, we can write this as two functions, which is f of x equals u to the 9th, or I guess x to the 9th power. G of x is equal to x minus 2 times 2x plus 1. So again, we have to find the derivative of the inner function, and here we can use the quotient rule. And again, remember the quotient rule is always just the bottom function squared over the top function, over the bottom function, times the derivative of the top function, which is just 1, because remember power rule, minus the top function minus the bottom function, or times the bottom function differentiated. So it looks like this. The x's cancel out, giving us 1 over 2x plus 1 squared. So just simple algebra there. So now we have the derivative of g of x, which is just equal to this function down here. And remember that the chain rule says that you take the derivative of the outer function, which is the x to the 9th, because that's the one we evaluate at the end. So it's going to be 9 to the 1 divided. Oh no, we don't change it, because we don't change the input, remember. So it's going to be x minus 2, 2x plus 1 to the 8th times the derivative of the inner function, which is this right here, which is just going to be 1 over 2x plus 1 to the squared. I can use some simple algebra here without having to expand, and apply the power to the both top and bottom. 8th, and then this would be just 2x plus 1 to the negative 1th. 2x plus 1 to the negative 2 power. Use some simple algebra at 9 minus 2 8th to the 2x plus 1 to the 10th, or you can move this to the top and negative 10th. But that is your differentiated function there. But that's so beautiful, so it's pretty simple. And yeah, that's all for the chain rule. So